Hello, everyone. My name is Jen Glick. I'm a quantum applications researcher at IBM Quantum, and today I want to talk to you a bit about how we can start thinking about using quantum kernels in practice. There's a couple of key ideas about quantum kernels that I want to revisit before we get started, and you may have seen these in previous lectures, so this should be a recap. So the first idea is that variational quantum classifiers are really just linear methods in quantum feature space. So that means we should be thinking about using quantum kernels as a similarity measure for our data. Second key idea is that quantum kernels, we can really only expect them to do better than a classical kernel if they're hard to estimate classically. And this is a necessary condition, but certainly not sufficient for some kind of computational advantage. And so, some of the quantum kernels that you may have seen before can be rather ad hoc. And so this means that we can't, even if they're hard to estimate classically, we can't necessarily expect them to perform well in practice on a given data set. So then how can we think about using quantum kernels in practice? So in classical machine learning, there are lots of ways to choose kernels. There's various optimization procedures like boosting approaches or rules of thumb to keep in mind when picking kernels. And in the case of quantum kernels, there's a few different things that we could try. And so what I want to describe is a couple of ways that we might approach this. And what we can do is we can create an ansatz for the quantum circuit that we use to calculate the kernel matrix. And then we can try to optimize that ansatz. So there's a few specific things that we could try. One is to take a quantum kernel that we know is hard to estimate classically. We could give it some kind of parameterization and then optimize it according to some cost function. An example of this could be the forylation kernel that you may have seen before. So this is a quantum kernel that's based off of the threefold forylation circuit, and it's related to a circuit family that's known to be hard to estimate classically. And so you could take this circuit and maybe add some tunable parameters to it and then optimize it. Another approach could be to take a quantum kernel that's easy to estimate, add some, make it a little more non-trivial, add some entanglement, and then parameterize and optimize that. An example here could be the Gaussian kernel. There's a third approach that I want to discuss, and it's an interesting approach because these first two ideas that I just mentioned, they're not necessarily guaranteed to work well in practice on any given data set. And so another way that one might think about using quantum kernels is seeing if there's some kind of structural insights in your data that you can exploit in designing your quantum kernel. So for example, you might think of symmetries in your data. And an example of this is the DLOG kernel. And this kernel, which you may have heard of in the previous lecture, is based off of the discrete logarithm problem. And this is an interesting kernel because it really exploits particular kind of structure in this learning problem. And it offers a super polynomial speed up over any classical learner for this particular problem. And so we're going to come back to this in more detail later, but I just want to give sort of a sense for where we're headed. So the main takeaways that I want to discuss today is a couple of things. So the first is, which we already touched on a little bit, any kind of ad hoc quantum kernel, even if it's hard to estimate classically, there's no reason why we would expect it to perform well on any given data set. And so that, that raises the question of, well, then, how can you think about using or picking a quantum kernel in practice? And one way that we could do this is to exploit some kind of structure in the data. And what I want to show you in more detail is, in particular, looking at data that has a group structure to it. And I want to show you that this, can be a promising approach because it includes a particular instance of a kernel that leads to a quantum speedup. And this is this D-log kernel that I mentioned on the previous slide. The second thing I want to discuss is we can optimize quantum kernels with a technique called kernel alignment. And so this kind of gives us an extra tool in our toolbox for designing kernels on particular data sets. And so what I want to do is I want to start with a really simple example of just a single qubit on a really simple data set. And I want to show how we can think about building and designing the quantum kernel for this data set that has a particular group structure to it. So for this example, I want to define a data set that has a group structure to it. I want to define what the classification problem is for this data set. And then we'll look at how you can build the quantum kernel to classify samples from that data set. And so what we'll do first is we'll look at a particular group. And so a group, if you're not familiar, you can think of it at a high level as just a set of elements and then some rules for combining the elements of that set. And so the group that I want to consider here in this example is SU2. And this is, you may be familiar with this already. It's the special unitary group. And it's the group of 2x2 unitary matrices with determinant 1. And, for example, arbitrary single qubit rotations can be represented as an element of SU2. And what we'll do is we'll look at what's called a subgroup of SU2. And a subgroup is itself a group that contains some elements from the larger group, in this case, SU2. And we'll use that subgroup to define our binary classification problem. So the particular subgroup that we'll look at, which we're calling S here, it contains 3 elements. So one of the elements is the identity, and then it contains an A and an A squared. And these elements, we can represent them by unitary matrices. And so, for the first element, which is just the identity, we can represent that by a 2x2 identity matrix. Pretty simple. For the other element, A, we can represent that also by a 2x2 unitary matrix. In this case, it is the exponential of a phase and the Pauli X gate. And this is, you can think of this operator as a rotation in around the x-axis by an angle of 2π/3. So we've defined a group and then a subgroup. And what we're going to do is we're going to create what are called left cosets. And cosets are just sets of elements in the group that can be used to break the group up into disjoint subsets. And these disjoint subsets or cosets are what we're going to use to denote the classes for a binary classification problem. So the elements of one coset will correspond to the +1 class label, and elements of the other coset will correspond to the -1 class label. Okay, so to create our cosets, what we do is we draw 2 elements from the group G, and we will take those elements and we will write down their unitary representation. So the first element, G1, is we're just going to pick the identity. And then the second element will be the Hadamard matrix, which you may be familiar with. We'll take these elements and we'll use them to define our 2 cosets. So the first coset, which is denoted by this C star, will be created by taking this first element G1 and acting on our subgroup. So if you work that out, you'll see that this coset is just composed of 3 elements, and it's the identity A and A squared. Pretty simple. And then the second coset, C dot, is formed by using the second element G2 acting on the subgroup. And so if you work out this, where G2 is the Hadamard matrix, then you get the following 3 elements, H, HA, and HA squared. And you'll notice that these two cosets are not the same. The elements are different. So they are indeed distinct sets of elements from the larger group. And so now that we've defined these, distinct set of elements, these 2 distinct set of elements, what we're going to do is we're going to use these to define what our binary classification data set is. So if we look at, let's just enumerate the elements of these cosets. So in red here are the 3 elements of our first coset C star, and we will say that these correspond to the class label +1. And then we have in blue the 3 elements of the coset C dot, and we will assign those the label -1. And these labels will use the common notation of Y to denote the labels for each of the elements, and then X sub I will denote an element from one of the cosets. And so our data set is just the set of pairs of these samples, Xi, and then their labels, Yi. So at this point, everything's a little bit abstract. So we can try to get a little bit more insight into what this data set is by trying to visualize it. And so the way that we'll visualize it is we'll take each of these elements, each of these data samples, which are really just single qubit operations, and we'll act on a quantum state with them, and we'll see what happens to the quantum state when acting with each of these elements. And so if we do this, we have to pick, on which quantum state do we want to act? So let's start simple and let's just pick the 0 state. So the question we're asking is what happens if we take the elements of these cosets and act on this initial quantum state? So if we looked at the first coset C star, we want to look at what is the unitary representation for these coset elements and how they act on the 0 state. And so these elements, as you may recall from the previous slide, they're composed of the subgroup elements S sub I and these 2 group elements G1 and G2 that we drew from the larger group. And so we have these 2 unitary matrices for G and S, and we act on the 0 state. So if we write these out for the 3 coset elements, we have the identity acting on 0, we have A acting on 0, and we have A squared. And as a reminder, A is just, you can think of it as a rotation around the x-axis. And so, you could work out the details of what these states look like. We won't do it here, but that's straightforward to do. The second coset elements, same thing, except now we look at, we'll be using G2 because that's what we use to define this coset. And these are the 3 elements, how the 3 elements of this coset act on the 0 state. Okay, and so what we can do is, because we're just working with a single qubit, we can actually just go ahead and represent these states as points on the surface of the Bloch sphere. This will give us a little bit more intuition about what's going on here. So if we look, here's the Bloch sphere for this single qubit, and there's 6 points on the surface of the sphere, and these represent these states that we just calculated. So let's go through which ones correspond to which. So in red here, we have the points that corresponded to this first coset C star. And you'll see that they live on an equilateral triangle with the points on the surface of the Bloch sphere. And if we did the same thing for the other coset C dot, then these live on this blue triangle. And these two triangles are orthogonal to each other, and they share a common centroid. And so what you can see from this is that, if you think about it for just a little bit, you'll realize, these two classes of data, they're not linearly separable in this space as we're representing them. So in other words, there's no plane that I could draw that can cleanly separate the blue points from the red points. And that means if we were to build a linear classifier in this space, that it would not perform very well because we can't separate this data. So maybe the next question is there a way to make this data set linearly separable? And so then the next question might be, well, what is the degree of freedom that we have in this problem? And you might remember we sort of arbitrarily picked the initial quantum state. And so perhaps if we picked a different initial quantum state, we could make this data set linearly separable. Let's try that. So let's suppose we tried a different initial quantum state. We'll pick the plus state, which is just the uniform superposition of 0 and 1. So let's go through the same procedure again. We'll see how the elements of each of the two cosets act on this quantum state. And so for C star, we do the same thing, but we replace 0 with the plus state. And if we write out the three states we get, we'll see something interesting. So we have, in the first case, we just have the identity acting on the plus state, which is the plus state. And then we have the matrix A acting on the plus state. And because A is a rotation around the x-axis and the plus state is on the plus axis, we actually just get the plus state back again. And so and then the same reasoning holds for A squared. So as you can see, something kind of interesting is happening. All of the elements of this coset just return the same state plus back. Okay, so then what happens with C dot? So if we look at this one and we write out the three different states, in the first case, we have the Hadamard acting on the plus state, and you might recall that the Hadamard just flips that back to the 0 state. And then if we look at the next element of the coset, which is H times A, remember A just is a rotation, it gives a phase, but it leaves the plus state the same. And so then we're just acting with H on the plus state, and that flips it back to 0. And then the same reasoning holds for H A squared, the third element. So now all of the elements of this second coset C dot, they all get mapped to the 0 state. And so that's really interesting. And then if we look at how this looks on the Bloch sphere, we see that all the elements of the first coset C star, they all group together into one point, which is on the plus x-axis, and all the elements of the other coset get mapped to the 0 state. And what that means is that if we wanted to build, a classifier model with this data set, all it would really have to do is distinguish between two data points. And that means that this is easily linearly separable. And in fact, in gray here, I'm showing a disk, which represents a separating hyperplane. And that means that a linear classifier on this data set will perform very well because it cleanly separates these two groups of data. Okay, so this is really interesting. What we basically saw is that the initial state that we picked for this particular data set with a group structure, um, the way that it looks really depends on which quantum state we picked for it to act on. And you might wonder, like why is this happening? What is it about this quantum state that's making this happen? And so it turns out that this plus state is what's called a subgroup invariant state. And in technical terms, what that means is that if I take any of the elements of my subgroup and I act on the plus state, I just get that same state back for every element in my subgroup S. And so in that sense, it's subgroup invariant. Now, if we look at how does an element of a coset act on this state, remember that the coset is formed from a subgroup element and the group element G. And so because U of S acting on our subgroup invariant state just returns the same state back again, all we are left with is the representation of the group element G acting on the plus state. So that means that if we were to think about, what is the quantum feature state for these data points, for all of the elements of the first coset that was formed with this element G1, they all just get mapped to this plus state for every element in the coset, because this plus state is a subgroup invariant state. For the second coset, which was formed from this group element G, we're left with just the Hadamard acting on the plus state, and that flips the plus state to the zero state. So every element in the second coset all get mapped to the same state, which is the zero state. So what we've seen is that the quantum state that we pick for this particular data set with group structure really matters. It can make the difference between making data that's completely non-linearly separable to being easily linearly separable. And so what I want to do next is I want to, make the connection between this and what the actual, how we calculate the quantum kernel for this. What does the circuit look like? How do we write down what the equation for the kernel is? So the feature state is defined, which we kind of saw in the previous slides, defined with respect to this initial quantum state, which I'm calling here psi, and then the unitary representation for our data samples, x sub I. And, in general, we could make the assumption that this state psi is prepared by a unitary circuit V acting on the zero state. And that means that if we want to calculate the kernel matrix, what we just do is we take this feature state for a sample x sub I, and we do the trace inner product with another feature state. And if you work out the details of this, you can show that you can write this as this transition amplitude shown here on the right. And so if we want to calculate the kernel or if we want to draw the circuit for this kernel entry, it's very straightforward to do looking at this as a transition amplitude. So what we would do is we would apply the circuit V, which prepares our initial quantum state psi, and then we would apply the circuit U of xj, which represents the one of the coset elements. And then we'd apply the inverse for another coset element, and then the inverse of this circuit that prepares our initial quantum state. And then once we've done that, we we make a measurement in the z basis, and we estimate, what was the probability of measuring 0, and that gives us an estimate for the kernel matrix entry for these 2 data points. So, everything that we've discussed so far in this example is pretty simple. It's a single qubit, it's a small data set. So one might wonder, is this a promising framework? And can it be generalized to a more general framework for more general data with group structure and other kinds of data sets and other kinds of kernels? And the answer is yes. And what I want to do is kind of go into a little bit more detail about that in the next few slides, but I want to give a little bit of terminology first. We call this initial quantum state psi, we call this the fiducial state. And we call the corresponding kernel a covariant quantum kernel. And the reason for this is because these kernels, they're connected to what's called covariant POVMs. So, coming back to this question of, could this be a promising framework to think about designing quantum kernels that are exploiting group structure in data? And there's good reason to believe that the answer to that question is yes. And the reason is because, in the previous lecture, you heard about a kernel that was based off of the discrete log problem. And so it turns out that you can view this kernel as a covariant quantum kernel. So this particular instance actually fits into this more general framework of kernels that exploit group structure in data. And this kernel was interesting because it's shown to lead to a polynomial speedup over all classical learners for this particular problem. And so what that means is that this framework is really interesting because it contains a known case of a really promising, a kernel that has been shown could give a super polynomial speedup for this particular problem. And I'm not going to go into any of the details of this kernel, but just to make a little bit of a connection to what we're talking about here. So this kernel was defined relative to a group called Z star P, and this is the set of integers with multiplication modulo P, and in this case for a prime number P. And this is interesting because this kernel was designed to be able to really take advantage of this group structure in this learning problem and give a nice computational advantage. And this is linked back to the idea that Shor's algorithm can efficiently compute the discrete log of the data samples, whereas classically this is very difficult to do. If you're interested in getting into more of the details, here's the reference on the bottom left for this paper. So before we move on, I want to sort of pause here and summarize a couple of points that we've been discussing. So we have good reason to believe that this framework of covariant quantum kernels, which are kernels that exploit group structure in data, is a promising avenue to investigate further. And one of the reasons is because it, as we just discussed, it contains a known instance of a quantum kernel with a quantum speedup. The second point, which we sort of observed already through this simple 1 qubit example, is that this fiducial state, it's really a key piece of this whole framework, and it may depend, the form of this fiducial state may depend on the particular learning problem and data set that we're trying to solve. And it also plays a really important role in the performance of the classifier. So, as we saw in this example, a bad fiducial state makes this data set completely unseparable by a linear classifier, whereas a good fiducial state makes it trivially separable. So the second point, this raises a natural question, which is then, well, how do we pick the fiducial state? And what I want to do next is kind of walk through one approach that one can use to address this question. And so the way that we'll start doing this is to sort of take a step back and recall some insights from training in SVM and use this to extract some kind of insight into how we could then find a good fiducial state for these covariant quantum kernels. And what we want is an approach to finding the fiducial state that could lead to good classification performance on a data set. And so then, the question is, well, how might we quantify classification performance? And one standard way to do this is through what's called the generalization error of the classifier. And the generalization error is basically the probability that your classifier misclassifies test points. So let's start by looking at the generalization error for an SVM. You might recall that the SVM can be viewed mathematically as minimizing a primal cost function. And so what's really interesting here is that if you look at the generalization error and if you try to place an upper bound on that generalization error, you can show that the primal cost function appears directly in that upper bound. And here in this first equation, what little m is the number of training samples for your data set, and then the O tilde just represents that we're ignoring any polylog factors in this bound. So you can show that for the SVM, placing the upper bound to the generalization error can be written in terms of this primal cost function. And what we do with the SVM is we want to find an optimal hyperplane. And so this primal, it holds for any hyperplane. And so what we can do is just go ahead and pick what was the best hyperplane, which is what the SVM is doing anyways. And we can rewrite this upper bound in terms of the minimum of the primal. So we're picking, what was the best hyperplane that minimized this primal cost function. So what this shows is that there's a connection between training an SVM and how well it might generalize to new data. Now, you might also recall that the SVM is a convex problem, and so we can think about minimizing the primal cost function, or equivalently, we can think about maximizing the Wolf dual cost function. And the solution from minimizing the primal is the same as that from maximizing the dual. And so we can rewrite this bound in terms of the maximum of the SVM dual. And this dual is, I'm noting here as an F of alpha, where you may recall that the alphas are the Lagrange multipliers in this cost function. And more explicitly, F of alpha is written out as this expression here, a summation over these data samples. Y sub I are the labels, and then K is the kernel matrix for an Xi, Xj data samples. And so this, this expression, it holds for any given kernel matrix that we pick. And so maybe a natural next question would be, could we get an even better bound to the generalization error by optimizing the kernel? So could we, parameterize this kernel matrix and then minimize the cost function over those kernel parameters and make an even better upper bound to the generalization error? And so the answer to this question is yes. And there's actually, the procedure that we would take is to solve this min-max problem of the Wolf dual cost function. And it turns out that this is actually connected to a well-known procedure called kernel alignment. And so we can think of this second summation in the Wolf dual cost function as a kind of weighted kernel alignment. And what this, if you kind of think about this more intuitively, what kernel alignment is doing is it's taking a parameterized kernel and it's trying to adapt the kernel to some underlying data distribution. And it's doing that in such a way that only the data points, which are the support vectors corresponding to non-zero alphas, determine what these kernel parameters are. And so what we can do then is solve this min-max problem where we parameterize the kernel matrix, and it will give us a better bound on the generalization error, meaning that our classifier is likely to perform better on a given data set. And there's a sort of another way of thinking about this, which is that kernel alignment, you can view it as a way to pick a kernel amongst a set of available kernels, the kernel that yields the smallest upper bound to the generalization error. And that's a really interesting way of thinking about this, procedure called kernel alignment. And to make the connection back to these covariant quantum kernels that we've discussed, we can use kernel alignment to find a good fiducial state. So what we can do is we can parameterize this fiducial state, and then we can solve this min-max problem, which is a kind of weighted kernel alignment, in order to find a good fiducial state. So this kernel alignment approach, it's an iterative procedure where we want to parameterize the fiducial state, and then we want to use classical optimizers in order to tune what good parameters for that fiducial state might be. And so the word good here is referring to this connection between kernel alignment and the generalization error of the classifier. So let's look at what the quantum circuit looks like for this single qubit example that we've been discussing so far. So it's we can think of kernel alignment in this context as just parameterizing our fiducial state. So here I'm showing some parameters lambda on this circuit V, which is what prepares our fiducial state. And what we would do then in practice to solve this min-max problem is we could use our quantum computer to estimate the kernel matrix and then feed this information to a classical computer to perform, an optimization and get updated parameters lambda for the kernel, and then iterate on this in order to find a good set of parameters for this kernel on a given data set. And so, kernel alignment it's a pretty general approach. It's not specific to these covariant quantum kernels. And it can be applied to lots of other kinds of kernels. Um, I want to give one example here, which is the quantum kernel based off of the threefold correlation circuit. And this is the sketch of what this circuit looks like for calculating this kernel matrix. And so what one thing you could do is you could take all of these single qubit gates, which were Hadamards, and you could just replace them with some single qubit rotation that's parametrized by an angle lambda. And then this is a way of taking this kernel and maybe adapting it to a particular kind of data set. So I want to summarize a few of the key points here in this lecture before we close. And, this first one, going back to the beginning, is that a lot of these variational quantum classifiers, we can really just think of them as linear methods in quantum feature space. And so, a good way of thinking about this then is using quantum kernels and using quantum kernels as a kind of similarity measure on our data, and as a way to kind of exploit or extract some kind of information about our data set in a way that we couldn't do with a classical kernel. And the second key idea is that these quantum kernels, they have to be hard to estimate classically. Otherwise, we could just use a classical kernel. And, of course, this is necessary, but a necessary condition. But on any, if you give me some, random data set, even if I have a kernel that's hard to estimate classically, it's not guaranteed to give me a good performing classifier. And so one approach to addressing this next question of how to make these practically useful is trying to design quantum kernels that take advantage of structural insight in your problem. And in particular, in this lecture, we discussed group structure and data, and a simple example of a data set that has that kind of structure, and then how to think about building a quantum kernel in that framework to exploit that structure. And then the last thing is that we can use this well-known procedure called kernel alignment to as another tool in our toolbox to optimize quantum kernels on a given data set in a way that can improve the generalization bounds of these classifiers. All right, that wraps it up for this lecture, and thank you all for watching.